screen now. Share the screen. Okay. So how many students are here? A few students are here. The rest will join soon. It's 3 o'clock, so we can start now. So last time what we were doing is that we were doing the final stages of our quantum mechanics chapter. Okay? So did everyone understand what we were doing last time? We were doing the finite potential well, and before that we were doing the infinite. Before that we were doing expectation values of the momentum operator and the position operator, and we also did the infinite square well before. So the finite potential well, we haven't really finished it, in a sense that the more details of this topic will come in the quantum mechanics course when you will study that in your senior year. Okay? So up till here, I can ask you to solve it up till what we have done in this, because the book also doesn't go into that much detail, and more details will come in the quantum mechanics course. तो यहाँ पे Schrödinger equation use करके उसको psi के जो psi 1, psi 3, psi 2 ये जो हमारे पास psi's हैं, इनको यहाँ तक I can ask you to derive it, ठीक है? Which is very short, but to find A, B, C, G, and these constants, ये अभी इस वक्त हमारे course के लिए नहीं है, ठीक है? So we will basically, what you will do afterwards in the quantum mechanics course is that we will apply boundary conditions. We will apply the boundary conditions for psi and d psi by dx, because both of them are continuous at x is 0 and x is L. तो ये हम ज़्यादा quantum mechanics में करेंगे next year, ठीक है? अच्छा, अब हम harmonic oscillator का topic करेंगे. What do you all know about harmonic oscillator? Have you all heard about a spring? So like if you have a wall, ठीक है? यहाँ पे एक wall है और यहाँ पे हमारे पास एक spring आता है, ठीक है? एक spring, ठीक है? And then we have a mass at the end of the spring. We have a mass at the end of the spring. It's connected to the spring, so that if this is the equilibrium position, ठीक है? This is the equilibrium position of the spring. When we apply a force on the mass, ठीक है? Force, the restoring force, it will be elongated. The spring will be stretched like this, for example. And now this is the maximum amplitude, for example. And then when it returns, so it's going to oscillate, right? When we pull the spring, pull the mass in this direction, for example, a distance A, it's going to oscillate about its equilibrium position, right? Because there's a restoring force that's going to want to bring it back to its equilibrium position, right? And what is the magnitude of the restoring force? We call it F is equals to kx. Okay, where k is a force constant. So let me go back to the slides. Okay, so harmonic oscillator is basically when you have a spring and one end of the spring is, say, connected to a wall, the other end of the spring has a mass attached to it. Okay, so this is a situation which is also important in quantum mechanics. We study about the harmonic oscillator in quantum mechanics. Why? Because it's interesting to us in many ways. Okay. So the restoring force of the particle is proportional to the particle's displacement. The restoring force is minus kx. Why is it minus? Because it's in the opposite direction. If this is the positive x direction, this is the positive x direction, and this is the positive y direction. We don't care about the y direction actually for now. We're only talking about the x direction. Okay? So if the force is in the positive x direction, which is this direction, okay, the restoring force is going to be a minus kx. Restoring force will be minus kx. Why is it minus kx? Because it's in the opposite direction. It's trying to bring the mass back to its equilibrium position, which is this one. And so what is the mass going to do? It's going to oscillate about the equilibrium position. Like it will go here. Like we pulled it in this direction, it will come back to this direction, then it will go back here, then it will come back here. It's going to oscillate repeatedly like this and like this and like this. Okay? So we want to apply the Schrödinger equation, write the Schrödinger equation for the situation. Okay? So according to Hooke's law, we have F is equals to minus K of x. Okay? this is scientist Hooke. He wrote this Hooke's law, okay, where F is proportional to the displacement. So we have, where K, what is K over here? K is the spring constant, or you can call it the force constant. It depends on the properties of the spring, of the spring, yeah. Okay, so it's like a proportionality constant, and the amount by which the restoring force is the value, magnitude of the restoring force depends on the spring constant as well as the displacement from the equilibrium position. Okay? So according to Newton's law, second law of motion, we have F is equals to ma. So if F is equals to minus kx, if F is equals to minus kx, okay, then we have F is equals to ma, so minus kx is equals to m times d square x by t square, because acceleration is given by d square x by dt square, right? You all know this, I suppose. So now, what are we going to do? Now what are we going to do is that we want to write down this equation is a differential equation, okay? This equation is a differential equation. We haven't yet used the Schrödinger equation as yet, ठीक है? Schrödinger equation में बाद में आएगा, ठीक है? So इस equation को, this is a differential equation, so how are we going to rewrite it in this form? And there are various ways to write the solution of this differential equation, ठीक है? One of the solution is to write it in this form. X is equals to a cos 2 pi f t plus phi. Where here 2 pi f, this nu is f. This nu is frequency. So frequency here, you must have all heard about the properties of a spring, right? Omega. The angular frequency of the spring is given by square root k over m. ये आपने oscillations या waves and oscillations के course में पढ़ा होगा थोड़ा सा, right? No? ये equation से आपको पता है ये कहाँ, ये कैसे आया है? The angular frequency of the spring is equals to square root k over m, where k is the spring constant or the force constant, and m is the mass that is attached to the spring. ठीक है? So
न्यूटन के लॉ को और स्टोक्स लॉ को इक्वेट करके आया है.
Stokes law, okay, well, yeah. जो भी जिस तरीके से भी आया है, we know that for the spring, this is the equation that holds for the spring, ठीक है? And we know that is equals to 2 pi times f, ठीक है? 2 pi times f is equals to square root k over m, right? Right? So we can say that frequency, which is given by nu, is equals to 1 over 2 pi square root k over m. ठीक है? So this is f or nu, which is equals to 1 over 2 pi square root 2 over m. ठीक है? So we write it in this form, and one of the solutions of this differential equation can be written as x is equals to a cos 2 pi omega 2 pi f t plus phi. And we already said before that solution waves can be written in this form, right? Where it's a is the amplitude and we have cos omega t plus phi. Where what is phi here? Phi is the phase difference. What does phi depend on? It depends on if like phi will be 0 if at time you have to put the value of t in here, like and the direction of motion. Okay? Phi, the value of phi, the phase angle depends upon what x is, what the position of the particle, the position x is of the mass that's attached to the spring at time t is equals to 0 and on the direction of motion. Okay? So for example, if at t is equals to 0, you have x is x is say 0.5 meters, okay? X is 0.5 meters, for example, and then you will put it in here, or x is 0 at time t is equals to 0. So then cos, you will apply the cos rule here, cos a plus b क्या होता है, और इसको expand करके. But that we're not going to go into those details. But over here, basically phi is the phase angle, which depends on what the value of t is and what the value of x is at the when t is 0, where the particle is at that time. Okay? So then we have this this frequency can be written in terms of k and m like this. Then we also know that for a spring, minus, if you take the integral of the potential energy is what? According to Hooke's law, the potential energy is minus times the integral of the force, right? Because we know that F is equals to what? Minus du by dx, right? But where U is the potential energy, right? You say yeah? So basically we will put here minus kx for the force and dx here. Integrate this with the minus sign is equals to u. ठीक है? From 0 to x. Is this making sense to everyone how we got this equation? समझ में आ रहा है सबको?
Yes, ma'am.
Okay, so this will be, now when we integrate this, the minus sign cancels with the minus sign, and we get half kx squared. Oh, wait a minute. Wait a minute. Half kx squared. How did the half come over here? Oh yeah, because of the integration, okay? So basically we get here kx squared over 2. Kx squared over 2, yeah? Kx squared over 2, and here we put in the limits 0 to x, okay? So we will get half kx squared basically. Half kx squared we will get. This is our potential energy for a spring. So now we have found the potential energy of a spring. Can we apply this to the Schrodinger equation? And if we draw a curve, if we want to sketch the potential energy as a function of x with respect to x, then we will get a parabola that looks like this. A parabola, half kx squared, will be drawn like this. Where over here, if we have x is equals to positive a or x is negative a, that is the amplitude of the oscillation. This is this value a here. Is this value a here. This is going to be minus a from here to here. From, if we erase this distance over here, this is minus a, and this distance, this is positive a. So that is the amplitude of the oscillation. Okay? So this is like the curve that looks like that is a sketch of the potential energy. And before we make a detailed calculation, we can anticipate 3 quantum mechanical modifications to this classical picture. Okay? ये हमारे पास classical mechanics में potential energy is going by a range of values. ठीक है? Range is taking a continuous values. The allowed energy will not form. So for the quantum mechanical spectrum, for the quantum mechanical case, the allowed energies will not form a continuous spectrum, but instead a discrete spectrum of certain specific energy values. The lowest allowed energy will not be E is 0, because obviously the lowest possible energy cannot be E is 0, right? It has some kinetic energy, it has some potential energy. So then E is equals to E naught will be the sum lowest energy. It will not be 0. There will be some probability that the particle can pass through the potential well it is in it and goes beyond the limits of minus A and positive A. Okay, so these are 3 assumptions. These are quantum mechanical modifications to this classical picture. And in order to understand the first quantum mechanical assumption modification, we have to use the Schrodinger equation. Okay, and then we will go to number 2, and then we'll check number 3 as well. So, so for the energy levels, now we have to try to find what the psi will be and what the energy levels are going to be for the harmonic oscillator. So according to quantum mechanics, we will not get a continuous range of values. Basically, this is the potential energy. This is not the energy of the particle. The energy of the particle is what we want to find here. The energy that corresponds to the size of the particle. So basically what we're doing here is that here the Schrodinger equation is what we want to solve, and here we're going to use the potential energy half kx squared. So we put that we have to write the Schrodinger equation. So how can we write the Schrodinger equation? Well, I don't really need to use a board here, but basically we have minus h bar square over 2m del square d squared psi by dx squared plus, well, I should write it, I guess. So, so यहाँ पे we are going to write here minus h bar squared over 2m d squared psi by dx squared, right? Plus half kx squared यहाँ पे होगा, right? Half kx squared because of the potential. This is our potential energy times psi is equals to E of psi. ठीक है? So when we rearrange the equation, we will get something that looks like this. ठीक है? And I'm not going to do all the algebra here because it's very easy. So when we rearrange the formula, we will get this equation. And then here you introduce y, you introduce dimensionless quantity y, which is equals to square root km over h bar whole power half into x, ठीक है? When we introduce this quantity, we will get this thing. K की value k times m square root k times square root k की जगह हम ओमेगा डाल देते हैं 2 pi times ओमेगा. यहाँ k को eliminate करके हम इस equation से k की value डाल देंगे. So it will be in terms k will be 2 pi square 2. It will be k square root k will be 2 pi f times square root m, right? So we put that value in here instead of for square root k. Then we will get something that looks like this, ठीक है? So we define an alpha, we define as 2e over h nu. ठीक है? These are dimensionless quantities that we are adding here, that we are defining here, so that we can make the solution of the Schrodinger equation easier, ठीक है? Therefore, the Schrodinger equation in terms of y and alpha, it can be written like this, ठीक है? When you introduce these quantities, it can be written as this, ठीक है? And the solution, now we're not going to go into the solution of this equation because it's going to be much more complex than we want, ठीक है? The solution to this equation is going to be complex. It's going to be complicated a bit, ठीक है? But that's not part of this course. But anyway, what I'm trying to say is that we also know that we have this normalization condition, ठीक है? That normalize, we want to basically what our goal of the harmonic oscillator and these finite potential well, infinite potential well, our goal is always ultimately to find the psi for the particle and the energies of the particle, the energies that correspond with each size. And the size are usually, they depend on n, which is the quantum number, right? So so this slide is actually not very important. There's the next two slides. I will only test you up till here, again. But basically what I'm saying is that if you have the normalization condition, which is the integration from minus infinity to infinity, psi whole magnitude squared dy is equals to 1, then you will, this condition has to be satisfied, okay? So this can help to find the normalization constant. And then the mathematical properties are also such that this condition will be fulfilled only when alpha is equals to n plus 1. Basically, ये ज़्यादा detail हम quantum mechanics के course में पढ़ेंगे, ठीक है? And I don't think I will expect you to know these 10. Slide number 10 and 11 are beyond like the scope of this class, but I will still tell you that that the energies of a harmonic oscillator go by n plus half times h f times h nu, ठीक है? और ये ज़्यादा detail बाद में करेंगे. लेकिन quantum mechanics के लिए बस यही है यहाँ तक कि E0, when you put n is equals to 0 here, when you put n is 0, that will give you the lowest ground state energy, which is E0 is equals to half h nu, half hf, ठीक है? And this is known as the 0 point energy because a harmonic oscillator will never have E is equals to 0. ठीक है? Because it will always have some kinetic energy or some potential energy at some point, ठीक है? So what I wanted to say here is that the derivation of this equation n plus half h bar omega, this will come more in your quantum mechanics course, okay? So up till slide number 9 is included in our course here. So I think we finished quantum mechanics. Are there any questions? Yes? Any questions related to the chapter of quantum mechanics overall? We had this this whole chapter here. So can we move on to our next topic, atomic structure? Atomic structure is also a long chapter. Yes? Are there any questions related to this topic, finite potential well or harmonic oscillator? Basically, for the finite potential well, if I ask you to, I will only ask you up till here, up till where we have done in class. And also for the harmonic oscillator, it's only up till 7, 8, and 9 slides, okay? Slide number 10 and 11. Slide number 10 and 11, that will not be included. But if you like, yeah, it won't be included because you should just know, I guess, that the energy levels of a harmonic oscillator go by n plus half hs, and the 0 point energy is when you put n is equals to 0 in here. That's the lowest energy. Okay, and you should also be able to write this equation, right? Like if I define these quantities, then you should be able to write the equation in terms of this. This is just algebra, basically. Okay, so I think we should move on to our next topic. Someone's mic is on. आप सब अपने mics off कर दें, बहुत शोर आ रहा है background से, yeah. Okay, so can we move on to our next topic now, I guess, which is atomic structure? Okay, we'll move on to our next topic, and I have uploaded this PowerPoint in the files of our class, okay, of MS Teams. So what do you all know about atomic structure? Any idea? So far, what we've been doing is we've been studying particle quantum mechanics, which is, we talked about the different possible, like here, if we go to the slide over here, we did relativity, which was when speeds go very high. We talked about quantum mechanics when the sizes go very small. And quantum field theory is the intersection between relativity and quantum mechanics. Quantum field theory is a total different course. But atomic structure is now the chapter we'll be doing. And this is a new chapter. It's chapter number 4 in the book. Chapter number 4 in the book of the modern physics, concepts of modern physics. And basically in this chapter, we'll be doing a lot about what properties of the nucleus. We'll be studying about the properties of atoms, the structure of atoms, Okay, most of them, we have atoms, and you all know that we have a central nucleus in the atom that consists of protons, neutrons, and then the electrons are in orbits around the, revolve or in orbits, different orbital levels around the nucleus, So we're going to talk about Rutherford scattering, which is Rutherford experiment, hua tha, and we'll be doing the Rutherford experiment, and with that we'll be deriving an equation for Rutherford scattering formula, and this equation, इसकी derivation काफी लंबी है, so just if you have questions along the way, you can always ask, okay? So chapters, we'll in this chapter and other chapters, we'll be concerned with the structure of the atom, okay? So why is it important to us? Is because everything is made out of atoms, okay? Everything is made out of these atoms, and every atom consists of a small nucleus of protons, neutrons, with a small number of electrons some distance away, okay? So we know that, we now know that that atoms consist of nucleus, a small nucleus, within which we have protons and neutrons, and electrons are not part of the nucleus, they are outside the nucleus, they revolve in orbits around. So most scientists in the late 19th century accepted the idea that chemical elements consist of atoms, but they knew almost nothing about the atoms themselves, So a lot of scientists before, they knew that elements were composed of atoms, but they didn't know what the atoms were made of themselves. So eventually electrons were discovered, They were discovered to carry negative charges, but we know that atoms are neutral in general, Atoms generally neutral होते हैं, जो उनके आयंस होते हैं जिसमें से इलेक्ट्रॉन रिमूव हो जाता है या ऐड हो जाता है, वो चार्ज होते हैं, So positively charged matter, so atoms are neutral, But we know that because they contain electrons which are negatively charged, they must also contain some positively charged matter, they must also contain some positively charged matter, but scientists did not know how they were arranged. So we're going to figure out how did scientists discover that how these atoms are arranged, basically how the electrons, protons, and neutrons are arranged in an atom. Okay? So Thomson was a British physicist who said in 1988 that atoms are positively charged lumps of matter. ठीक है? He said Thomson का मॉडल ये था, ठीक है? ये सबको नजर आ रहा है, ठीक है? Thomson का मॉडल ये था, which was more like a plum pudding model. That's what he said, ठीक है? That basically he said, yes? Someone saying something? Okay, so he said that there's a positively charged matter, ठीक है? Electrons are embedded in them as we have the atoms are just positively charged lumps of matter with electrons embedded in them like raisins in a fruitcake, okay? So he basically said that Thomson presented a plum pudding model sort of thing, in a sense that there's a like a pudding of positively charged matter. Usme electrons are embedded, equally distributed are in that matter, okay? So Thomson he did discover the electron, but his plum pudding idea was not actually his plum pudding model was not correct. It turned what the real model of the atom was later on to be discovered by Rutherford. So then we have the Rutherford experiment, where we have Hans Geiger and Ernest Marsden did an experiment in 1911. It was called the Rutherford experiment because Rutherford was the one who was supervising it. So at the suggestion of Rutherford, what Rutherford told them to use probes as fast alpha particles emitted by certain radioactive elements. Okay? So basically, fast alpha particles, this is the diagram for the Rutherford experiment. Fast alpha particles were used. They used a radioactive substance that emits alpha particles. Fast alpha particles were used in this experiment by using radioactive elements. And then alpha particles what are alpha particles? Basically, they're helium atoms that have 2 electrons with a charge, leaving them a charge of positive 2e, right? Alpha particles क्या होते हैं? Helium atoms that have lost 2 electrons, right? So 2 helium होता है ना, जिसमें alpha particles कौन से होते हैं? जिसमें 4 totally, like there are 2 protons, 2 neutrons, and 2 electrons, right? So alpha particles are helium atoms that have lost 2 electrons, ठीक है? So Geiger and Marsden placed a sample of an alpha emitting substance behind a LED screen with a small hole in it, so that a narrow beam of alpha particles was produced. Okay? So basically, this is the diagram of the Rutherford experiment that we have. Okay? So this is a LED, what do you call it? A LED wall sort of thing, a LED screen with a small hole in it. Okay? So that alpha particles could pass through the hole. Okay? So when they pass through the hole, then we have what we have here. There's a thin gold foil here. Okay? They placed a gold foil. The beam was detected at a thin gold foil, okay? Then we have a zinc sulfide screen which gives off a visible flash of light when struck by an alpha particle. It was set on the other side of the foil with a microscope to see the flashes. So we have here, this is our alpha particle Rutherford scattering experiment, where we have a radioactive source here, and which is emitting alpha particles, and we have a LED column, LED screen here, a LED sort of like a LED screen here, which has a hole in it so that alpha particles could pass through the hole. We have a thin gold foil here, and then we have a zinc sulfide screen like this, curved zinc sulfide screen, which would give a flash of light, every time it would be struck by an alpha particle. And then we can view the flash of light using the microscope, and the microscope is also movable. We can move it around here, okay? So this is the experiment. This is the experiment for the Rutherford's experiment setup. Okay? It was what's the expectation from this experiment? That the alpha particles would go right through the foil with hardly any deflection. Okay? Because if we have, according to Thomson's model of the atom, if we have a model of the atom that looks like a plum pudding shape, okay? मतलब कि इसमें एक पुडिंग है जो positively charged particles, positively charged protons वगैरह हैं, and उसमें electrons are embedded like equally spaced, ठीक है, like throughout the surface, throughout the volume of the positively charged material. So इसमें क्या होगा कि we would expect most of the alpha particles to go through the foil with hardly any deflection, ठीक है? Because why? Because they would just, yes?
मैम फिर तो डिफ्लेक्शन हम ऐसे क्यों एक्सपेक्ट करें कि विदाउट डिफ्लेक्शन वो जाएंगे, जब हालांकि इलेक्ट्रॉन्स भी मौजूद हैं और हमारा जो अल्फा
इलेक्ट्रॉन्स बहुत
पार्टिकल है वही
छोटे होते हैं ना, उनका मास, इलेक्ट्रॉन्स का मास बहुत छोटा है ना, तो उसके साथ इतनी ज्यादा डिफ्लेक्शन नहीं नजर आएगी।
सही
सही, तो इसमें ये कह रहे हैं कि we would expect that there would not be very much deflection, but from the Thomson model, yeah, it follows from the Thomson model in which the electric charge inside an atom is assumed to be uniformly spread throughout its volume. So that's what I said earlier. The Thomson के model में we would assume that the material, the electrons are uniformly spaced throughout the positively charged material. ठीक है? Throughout would be uniformly spread throughout its volume. With only weak electric forces exerted on them, alpha particles that pass through the thin foil would be deflected only slightly 1 degree or less. ठीक है? So basically the assumption is that what we're expecting from this experiment is that alpha particles would mostly pass through and deflected only slightly 1 degree or less due to the electrons that are placed uniformly throughout the material. उसकी वजह से deflection should not be very much, ठीक है? It should only be 1 degree or less. ठीक है? But what we actually found, this is the Rutherford model of the atom. Well, I'll come to this shortly. What Geiger and Marsden actually found was that although most of the alpha particles were not deviated by much, a few scattered through very large angles. ठीक है? So Geiger and Marsden, they found that most of the alpha particles did pass through, but some were scattered through very large angles. ठीक है? Some were even scattered in the backward direction. Like there was a diagram. Where is that diagram?
fully reflect हो गए थे।
Yeah, some were deflected very much backwards. Well, I have a diagram like this. ठीक है? This is not a appropriate diagram for that. But what I'm saying here is that some of them went here. I was over here. ठीक है? Yeah, they discovered that a few of them were scattered by very large angles. Some of them even were scattered in the backward direction. ठीक है? So alpha particles, how can we explain this theory? How can we explain this result? So alpha particles we know are relatively heavy, almost 8,000 times electron masses, and those used in the experiment have had high speeds, ठीक है? Like almost 2 into 10 raised to power 7 meters per second. ठीक है? It's clear that powerful forces were needed to cause such marked deflection. They had such high speeds, and they're relatively very heavy, like 8,000 times electron masses. ठीक है? So that means that if they were deflected by such strong, like something must have been very powerful that deflected it in the backward direction, or the ones that deflected by very large angles. So how we can explain that? Rutherford explained that result by his model, which was different from the Thomson model, and it was to picture an atom as being composed of a tiny nucleus, which is its positive charge, and nearly all its mass where nearly all of its mass is concentrated, with electrons some distance away. ठीक है? So the Thomson's model was quite different from the Rutherford's model. ठीक है? Thomson's model was like the uniformly spread, positively charged, and then there's negatively charged electrons were spread out uniformly throughout the material. So Rutherford's model says that there's a strong positively charged nucleus at the center of the atom, and all the rest of the electrons there are scattered like anywhere else outside the nucleus. Okay? This is Rutherford's model. And how can Rutherford's model explain our results? Well, atom is largely because of Rutherford's model says that the most of the mass of the atom is concentrated in its nucleus, right? Because we have protons, we have neutrons, they're heavier. Electrons are very light, okay? Electrons are not very heavy. So most of the atom is largely empty space, okay? This is the mostly empty space, okay? Where we have some electrons orbiting the nucleus. So with the atom being largely empty space, it's easy to see that alpha particles can go right through the gold foil. Okay? So the alpha particles, most of the alpha particles, that's why most of them just go through, they go straight through the gold foil. However, when an alpha particle happens to come near a nucleus, the intense electric field there scatters it through a large angle. Okay? Because a nucleus is like, it contains the protons, the neutrons, etc. And that's positively charged, right? We know that the nucleus is positively charged. So, and it's very strong forces in the nucleus. Okay? We have the strong force there. So strong forces are very strong in the nucleus. So when an alpha particle comes near the nucleus, the intense electric field there scatters it through a large angle. Okay? So the intense electric field will scatter through a large angle. So that's how Rutherford explained the Rutherford scattering experiment. The atomic electrons being so light do not appreciably affect the alpha particles. Okay? The electrons are very light, so they do not affect the alpha particles very much. Okay? So the deflection of an alpha particle when it passes near a nucleus depends on the magnitude of the electric nuclear charge. Okay? Depends on the magnitude of the nuclear charge. जितना ज़्यादा charge होगा उतना ज़्यादा उसकी deflection हो सकती है. ठीक है? Because जितनी ज़्यादा उसकी positive charge होगी nucleus की, उतनी ज़्यादा strong force होगा. ठीक है? Which is going to repel the incoming nucleus. So scattering उसी से होता है. ठीक है? So comparing the relative scattering of alpha particles by different foils thus provides a way to find the nuclear charges of the atoms involved. So if you have different foils, and different foils like gold foil है या silver foil या जो भी है, different elements, different materials के दूसरे foils हैं, then you can compare the relative scattering of alpha particles with those different foils, and thus you can find out how much nuclear charges are involved in the different foils that we are considering. Okay, so all the atoms in any one. So as we said before, wait a minute, just 1 second. Helium atoms have lost 2 electrons. We are concerned with alpha particles that are also positively charged because they have a charge of positive 2e, right? Positive 2e, because they have lost 2 electrons. Yes. So they're also positively charged, so they will be repelled by the positive charge of the nucleus. Okay, so now we are on the slide, and it says here that all the atoms of any one element turn out to have the same unique nuclear charge, and all the atoms of one element, एक ही element का अगर हम atom लें, for example, chlorine या कोई भी element ले लें, ठीक है? They all have the same unique nuclear charge, ठीक है? जिसमें कुछ number of protons होते हैं, nuclear charge में प्रोटॉन, न्यूक्लियस में प्रोटॉन्स होते हैं, न्यूट्रॉन्स होते हैं, उनके चार्जेस जो हैं उनको सम कर दें. न्यूट्रॉन्स आर ऑब्वियसली न्यूट्रल ना, तो प्रोटॉन्स का जो भी चार्ज होगा दैट इज द न्यूक्लियर चार्ज. ठीक है? And this charge increases regularly from element to element in the periodic table. You must have all studied periodic table in chemistry, right? So उसमें element to element उनके nuclear charge increase होता जाता है. ठीक है? The nuclear charge, the charge of the nucleus. ठीक है? So the nuclear charges are always turned out to be multiples of E. Okay? E is the electron charge. So basically, we know that the number Z of unit positive charges in the nuclei of an element is called the atomic number of the element. हमें पता है कि अगर एक element है, ठीक है? एक element है, उसको हम लिखते हैं, ये ज़्यादा nuclear जब चैप्टर करेंगे ना, न्यूक्लियर फिजिक्स का चैप्टर, उसमें ज़्यादा ये आएगा. लेकिन अगर ये एक सब्सटेंस है, कॉल इट AG for silver, and here is the Z, sorry, यहाँ पे M होगा. This is the mass number, ठीक है? यहाँ पे I think we use the symbol M or A here and Z here, ठीक है? Z is a proton number and this is the mass number, ठीक है? So Z is the number of protons in the nucleus, and M is the total number of neutrons plus protons. So that is the mass number. So we will study more about this in the nuclear physics chapter in the same course. Okay? We know the protons, each with a charge of E, provide the charge on a nucleus. The atomic number of an element is the same as the atomic number Yeah, so atomic number of an element is basically the number of protons in the nucleus of an atom. Yes? And basically each proton has a charge positive E. Positive E. Yes? Positive the charge of an electron. So ordinarily matter is mostly mostly empty space because the electrons, their masses are much smaller than that of the protons. And the protons are the ones that are in the protons and neutrons are in the nucleus. So now we have a Rutherford scattering formula, and its derivation is very long. Okay? The derivation of this Rutherford formula was going to be on throughout these slides. Okay? ये slide number 10 से लेके 23, all of these slides is for the derivation of this one formula. ठीक है? So Rutherford scattering formula, what can we say about this formula is the formula that Rutherford obtained for alpha particles. The formula that Rutherford obtained for alpha particles scattered by thin foil on the basis of the nuclear model of the atom is given by this formula. Okay? And what is this formula? What are these different symbols in this formula? Let's see that now. This formula is derived in the appendix to this chapter, and we're going to do that as well. Okay, it's going to constitute all these slides that we will cover in the next lecture mostly. But let's see over here. So the symbols in equation 4.1 have the following meanings. N theta is the number of alpha particles per unit area that reach the screen at a scattering angle of theta. Is this making sense? N theta is the number, n as a function of theta. Theta is what here? Theta is our scattering angle. So for example, if I have a diagram, where I can open that other diagram, like if we have the gold foil is here, ठीक है? उससे फिर scatter इतना हुआ है, ठीक है? So this is our scattering angle, theta, ठीक है? This is our scattering angle theta, and it will be shown in one of the this is our scattering angle. ठीक है? अगर alpha particle इस तरह जा रहा है और ये scatter इस तरह हुआ है, तो this is our scattering angle, which is taken from the initial direction to the final direction, the angle between the initial direction and the final direction. Okay? So that is our scattering angle, and n of theta is the number of alpha particles per unit area that reach the screen at a scattering angle. So basically, if we have this diagram over here, if we have a per unit area of the screen here, how many alpha particles reach the per unit area of screen over here at that particular angle? That is what n theta is. And we want to find a formula for n theta. And so it is this given by this formula here, sine power 4 theta divided by 2 kinetic energy. K is the KE is the kinetic energy of the alpha particles. Ni is total number of alpha particles that reach the screen, the total number of alpha particles that reach the screen. Small n is the number of atoms per unit volume of the foil. Number of atoms per unit volume of the foil. Okay? T is the thickness of the Z is atomic number of the foil atoms. R is the distance of the screen from the foil. Okay? So for example, if we have that diagram, go back to that diagram here. So R is the distance of the screen from the foil, whichever particular distance we are using. Okay? So this is a long derivation, so we will do this derivation. But let's see. So let's talk about, maybe we can do these few slides here because we still have some time. Okay? So Rutherford's model of the atom, it was accepted because ये हम equation हम सारे derive करेंगे, ठीक है? Maybe not all of it today, but we have the next class tomorrow. Yeah. So कल बाकी हम कल भी करेंगे, लेकिन we still have some time right now, so we can go on with 6 more minutes, ठीक है? So Rutherford's model of the atom was accepted because he was able to arrive at a formula to describe the scattering of alpha particles by thin foils on the basis. Basically, Rutherford's model, it was not just a theoretical model, but he also explained, he also derived an equation for the scattering of alpha particles by the thin foils on the basis of his model. Okay? So his formula, it agreed with experimental results, and therefore Rutherford's model was everyone accepted his model because it was it agreed with his formula agreed with the experimental results. So he began by assuming that the alpha particles in the nucleus it contains are both small enough to be considered as point masses and charges. Okay? So he made three assumptions in his model of the atom. One is that the first assumption is the alpha particle and the nucleus it interacts with are both small enough to be considered as point masses and charges. Okay? So we have to assume that the alpha particles in the nucleus are so small that we can consider them as point masses and charges. Number two, the repulsive electric force between alpha particles and the nucleus, which are both positively charged, is the only one acting. ठीक है? हम अभी के लिए Rutherford के scattering के formula के लिए and for the model Rutherford's model of the atom, we are making three assumptions, and the second of the assumption is that the repulsive electric force between the alpha particles and the nucleus is the only force that is acting between those two particles. Number three, that the nucleus is so massive compared with the alpha particle. ठीक है? Nucleus is so massive compared with the alpha particle that it does not move during their interaction. So these are three assumptions that we are making. These three assumptions lead to equation 4.1, which is this equation. And we're going to use these assumptions to make for our derivation. And this is just repetition of those assumptions. Okay? So now we will, the derivation is quite long, okay? And I don't know if I should go ahead with starting the derivation right now. We have like 4 minutes left, but we can go on the derivation, but it's quite long, so I mean, I don't know what all of you want. Should we start it off?
No, man.
No? Why? So it's
कल
quite
आराम से
long
करेंगे
and, huh?
कल करेंगे आराम से
Okay, so from slide number 13 to slide number 23, it's a very long derivation, okay? So yeah, we will do this. I guess we can do this tomorrow. Are there any questions related to any of the things we covered today, related to this atomic structure or to the quantum mechanics that we finished? Rutherford book का है chapter number 4. Chapter 4. अभी हमने कर लिया है. We've done. Let's see. We have done chapter number 1, which is relativity. We have done chapter number 3, which is wave particles and properties. We have done chapter 4, which is atomic. No, we have not done chapter 4 yet. Atomic structure हम अभी कर रहे हैं और chapter 5 किया है. तो हमने अभी तक chapter 1 किया है, chapter 3 किया है और chapter 5 किया है. We still have 4 more chapters to go. Atomic structure, nuclear physics का chapter इतना लंबा नहीं है, ठीक है? Nuclear physics का chapter, nuclear structure and nuclear transformations. वो इतना ज़्यादा लंबा नहीं होगा, I guess. One of the two chapters, nuclear structure, is not very long, but then atomic structure is a long chapter, ठीक है? And इसकी derivation काफी लंबी है, Rutherford scattering formula की, ठीक है? And then we have particle properties of waves. So we have, I think, 4 more chapters left. We've done 3 chapters. ठीक है? So ये syllabus थोड़ा सा ज़्यादा लग रहा है मुझे, लेकिन क्या हो सकता है, ये syllabus तो बना हुआ पहले से था, तो इसलिए we have to cover all these topics. ठीक है? Any other questions? So atomic structure is a relatively longer chapter. So tomorrow we will cover, hopefully we will cover all of this up till here, okay? The derivation of the Rutherford scattering formula, and then we have to do atomic structure, which mostly we have done a lot of some of these topics in astronomy and astrophysics, ठीक है? इसमें थोड़ी सी वो Bohr model of the atom आता है, वो तो derivation हमने पहले की हुई है उसमें astronomy and astrophysics में, ठीक है? तो इस चैप्टर में ज़्यादा आएगा, लेजर्स भी हमें करना होगा, इलेक्ट्रॉन ऑर्बिट्स थोड़ा सा पढ़ना होगा और एटॉमिक स्पेक्ट्रा होगा, बोहर एटम. थोड़ी सी रेपिटेशन होगी एस्ट्रोनॉमी और एस्ट्रोफिजिक्स की, which you already have a base on that. ठीक है? And then we will study lasers. Lasers is very short, not very long. ठीक है? So are there any other questions? So tomorrow we will continue with this. We will continue with the derivation on this of the Rutherford scattering model. ठीक है? Rutherford scattering formula. Yeah. 3:50. We finished exactly on time today. So, are there any questions, or do you want to? I don't know. I guess if you don't have any more questions, then we'll continue tomorrow. Okay. Let me see if I have downloaded the attendance list. Yes, I have. Okay, so tomorrow our class on Thursday, which was at 3 to 4, has been shifted to Wednesday 3 to 4. Okay, so I hope you all know that. Okay, Wednesday 3 to 4 will be our third class for the week. Okay, so I guess we're done with today's lecture, and if there are no questions, then I can just stop the meeting.
Yes,
Okay.
ma'am. Yes, ma'am.
Okay.
Okay.
Hafiz.
Allah.
Hafiz. Hafiz.